Hello, my dear students and the rest of the learners. Welcome to part 4 of a 22-part series of tutorials in Managed Database System using Microsoft Access and SQL. In this presentation, I'm going to be looking at database design concepts other than design basic database. My name is MemGM, or you can simply call me Emily Swap. Let's begin by looking at database design concepts. What is database design? Database design is the process of creating or formulating a database that will support the enterprise's operations and objectives. It is performed in 3 major phases or stages, which are the conceptual design, the logical design, and the physical design. Database design therefore involves defining tables, the fields, the primary keys, and relationships. When you are creating or designing a database, you need to think about what we call the entry or data integrity. Here, you put rules in place so that users can be able to enter correct values and deter any entry of the wrong data in the fields. The valid rules for a field, that is data type, input masks, and validation rules are set. An example is if, for example, you have a field called date of birth, then the data which is entered must be a date. So you set a format and validation rule that will ensure that whatever that is entered at the date of birth field is a date. If you are entering a phone number, you also need to have an input mask that will limit what will be entered so that the data which is entered can be in the format for phone number, whose format should be, as you can see, parentheses, 3 zeros, closing parentheses, space, 3 zeros, dash, 4 zeros. That is the format for a phone number. So this will ensure that the data which is entered is a number and the format is as you can see. Some access examples are field called date of birth, as we have said, which is supposed to be set to date, stroke type. So when we're ensuring that there's data integrity in your database, there are a number of things that you set, and one of them is determining the type of data that will be entered and the type. So for the field for date of birth, you have to set it to date stroke time type. If you have a field in which you are going to enter an email, there's also a format for the email and how it is supposed to look like, or what we call the validation rule. For example, like you type it this way, double quote, asterisk at, asterisk dot, asterisk. For example, an email like Julimenga at gmail.com. So the asterisks here, this means anything at anything.com. For example, Julimenga at gmail.com. Or another example would be Otieno1 at yahoo.com. So generally, the symbol at ensures that whatever you write, whatever you enter must have the at symbol, while the asterisk means anything but For it to be an email, it must have an extension dot something, .com, yahoo.com, gmail.com, or any other dot something. It can even be .ca.ke. So the format is that. So you have to set that field to be, or to restrict a person to entering data in form of an email. If you have a field for the form, just as I've said, you need to set the input mask to be that format. We also have what we call the entry or domain integrity. So we have data integrity, and we also have an entry or domain integrity. Under the domain integrity, we ensure that values in a column follows a defined data type and allowable range. For example, date of birth is date. Email follows the email pattern. In access, you set data type and a validation rule under the design view. So to ensure there is entry on domain integrity, for every field, you set its data type and a validation rule, and this is done and design view. We shall be doing this, don't worry. My dear viewer and my dear listener, don't worry. We shall do this, and we shall do it practically. We also have what we call entity integrity. Entity integrity is an attribute in Access that ensures that every table has a unique primary key that uniquely identifies rows and ensures that the primary key is not null. It ensures that no nulls in primary key fields. For example, student ID must be filled and unique because every data in a database for students must be identified using that student's ID, or in a real case, an admission number. Even products, every product must have its own unique ID. So unique ID cannot be empty. For example, student ID in student's table can be a primary key, and therefore it cannot be null because it must be used to identify the student. It therefore ensures that each record is uniquely identifiable. So that's the work of a primary key, and that key is not empty. Entity integrity ensures that each record has a unique primary key, while referential integrity ensures foreign keys match with valid primary keys in the latent tables. That's referential integrity. For example, immediately you set a field in a table as a primary key, for example, student ID, by right-clicking in table design and clicking on the primary key. Once you have done that, if there's student ID in another table, that other student ID or that other field should also be a key. So in one table, it will be called primary key. In the other one, it will be a foreign key. So Access automatically recommends auto number to avoid duplicates and manual errors. In other words, because one field must always act as the primary key, whenever you create a table, before you start even specifying or adding your other fields, Access will automatically add one field for you. And the value for that field will be a number. So it will be an auto number, and it is generated automatically as you add records. So Access automatically recommends auto number to avoid duplicates and manual errors. In entity integrity, primary keys must be unique. Let's also look at what we call referential integrity. What is referential integrity? This is setting rules that ensure relationships between tables remain consistent. That is, foreign key values must match primary key in parent table. For example, you cannot enroll somebody into a course if his or her student ID does not exist. And you cannot delete a course that is still linked to a student. Very important. An example is student course. A student course will have the firm's student ID and the course ID. Now, this requires that the student ID exists in the student table. So there's no way you can talk about a student pursuing a course, yet that student does not exist. So before a student takes a course, that student must exist. And that student is identified using a student ID, which must be in the student's table. Therefore, it ensures that a foreign key in a child table matches with valid primary key values in the parent table. This means that the primary key in the parent table cannot be null, and the foreign key cannot be null or empty. For example, program ID in students table must exist in programs table. It is enforced in relationships window. Options to cascade or update stroke delete. For example, you can prevent deleting a student record if they have enrollments, unless cascade delete is enabled intentionally. Another example from memory swap database that you're going to be creating would be enrollments.studentID. This means a field called student ID and enrollments table must exist in the table called students, because you cannot enroll somebody who does not exist. Therefore, students ID or student ID must exist in students table if that student has to be enrolled and details kept in the enrollments table. Therefore, to enforce referential integrity in an access database, you follow the following procedure. You click on tools, then you click on relationships. Then you click on create relationship and check enforce referential integrity. This prevents orphan records, and we shall do this in my subsequent presentations under creating of tables. So let's look at phase one when it comes to designing the database or database concepts. Phase one is called conceptual design. What do you do here? This is the process of constructing an abstract model of data to be included in the database. So you come up with model data. This data may not be real, but it has to resemble the real data in a real environment. So this model should be independent of any database management system. That means this model that you come up with should not be restricted or limited to a specific database management software. It should be in data which can be catered for, or this model should be a model with data which can be catered for using any database management system software and other physical considerations. So the steps followed for you to be able to design this conceptual design are as follows. Number one is you identify the entities that your database will have. Number two, identify the relationships that will exist. Number three, construct conceptual data model. So let's look at how you identify entities. Now, identifying entities is a thing or object of importance about which data must be captured. So you have to ask yourself, which entities will your database have? To identify the entities in the requirements, you map nouns to entities. If a student, student's entity, enrollment, enrollment's entity, fees, fees entity. Now, database entities appear in a data model as a rectangle with a title. If you have not seen how entities are represented, I would kindly refer you to presentation number 2 of this series and the presentation number 1, and you are going to see how we represented an entity, especially when we are representing the ERD. Now, the title, which is supposed to be in uppercase, is always the name of the entity. So every entity must have a title to be used to identify it in the database. Now, we have various types of entities. Now, number one, we have what we call the weak entity. What is a weak entity? This is entity that does not have sufficient attributes to form a primary key or unique identifier. So we don't use a weak entity as a primary key. The existence of a weak entity is indicated by a double rectangle in the R diagram as follows. So if an entity is weak, we use a double rectangle, or we use the symbol, which looks like two parallel lines around. These are like two rectangles in one, and we write it as weak entity. The second type of entity is a strong entity. A strong entity is an entity that has a primary key, that is unique identifier. Remember, a weak entity is existence dependent. So we have strong entity. Number three, we have what we call recursive entity. This is an entity in which a relationship can exist between occurrences of the same entity. This occurs in a unary relationship. For instance, a doctor can be a patient. A doctor can be a patient, and we can represent that this way. At one time, a doctor is a doctor treating a patient. But then, if the doctor is sick, he or she becomes a patient. So that's called recursive. At one point, you're in a status of a doctor. At the second one, you are as a patient. So when you have such an entity that can exist in more than one form, we call that one a recursive entity. A doctor treats a patient. A patient gets treated by a doctor. So when a doctor becomes a patient, he or she will also require to be treated by another doctor. So at one point, a doctor or a person is a doctor. At the other time, he or she acts as the patient. The fourth type of entity is called the composite entity. This is an entity which is created to resolve many-to-many relationships to one-to-many. It is also referred to as a bridge entity. Bridge entity is composed of the primary keys of each of the entities to be connected. And a composite entity can therefore be represented by a diamond shape with a rectangle in an entity relationship diagram. Now, generalization. The process of defining a more general entity type from a set of more specialized entity types is called bottom-up. Now, what about specialization? This is the process of defining one or more subtypes of the supertype and forming supertype or subtype relationships. And that is called top-down model. So in generalization, we have what we call bottom-up. In specialization, we have top-down. Let's now look at how we identify relationships. A relationship is a meaningful association between entity types. These relationships can be classified either according to their degree, their cardinality, or optionality. Remember, when you are creating a relational database, for example, using Access, you must have some relationships, or the tables must have relationships, so that at the end of the day, when each table is related to another or to others, we form what we call a database. So let's look at the classification of relationships according to degree. Degree refers to the number of entity types participating in a relationship. So the first type of degree is unary recursive relationship. Here, one entity type participates in a relationship. The second type is binary relationship. In binary relationship, two entity types participate in a relationship. And the example is there. Then we have what we call ternary relationship. Here, three entity types participate in a relationship. For example, a trainer, training and trainee, and you have an issue there. The fourth type is called an array relationship. This is where a number of entity types participate in a relationship. The second classification of relationships is according to cardinality or connectivity. In a relationship, cardinality refers to the number of entity occurrences involved in the relationship, also defined as minimum and maximum number of entity occurrences that can participate in a relationship. Some examples include one-to-one relationship, which we abbreviate as 1:1. Here, each entity occurrence in entity type A can only have one matching entity occurrence in entity type B, and vice versa. In other words, simply put, a single field in a single table is related to another single table or single field in another table. 1:1. One field in one table being related to one field in another table. And this is an example. It's an example of one-to-many. So these are two tables. So in table 1, table A, we have 4 fields. Field A1, A2, A3, A4. In table B, we have field B1, B2, B3, B4. So as you can see, in the first table, we have first field called A1 being related to only a single field. In table 2, B1. If we are letting field 2, then field 2 has only a single matching field in the second table, that is in the third table, etc. So each entity occurrence in entity type A can only have one matching entity occurrence in entity B and vice versa. So that is one-to-one. What about one-to-many relationship? In one-to-many relationship, an entity occurrence in entity type A can have several matching entity occurrences in entity type B, but each entity occurrence in entity type B can only have a maximum of one entity occurrence in entity type A. You can see the entity type A, entity A1, is related to all the entities in entity B. Let me put it in a simpler way. So the A1, if I was to look at A1 as a field, from the A1 is as a relationship with all the fields in entity B maximum. So we are saying that in one-to-many relationship, an entity occurrence in entity type A, as you can see, like A1, can have several matching entity occurrences in entity type B. But each entity occurrence in entity type B can only have a maximum of one entity occurrence in type A. You can see that. Like field A1 as a relationship with all the fields in, call them tables. A table A, let's assume, or let's say, the circle represents a table. So table A contains 4 fields. Table B contains 4 fields. Now, what is outstanding here is that the field called A1 is related or has a relationship with all the 4 fields in table B. But table B, or the fields in table B, have only a single relationship or a single field related to it in table A. So B1 has only a single relationship with table A, table B. So B1 field in table B is related to only one field in table A, A1. The same to field B2 is as only a single relationship with field, a single field in table A, as you can see. So that's what we call one-to-many. The third one is called many-to-many relationship. Here, an entity occurrence in entity type A can have several matching entity occurrences in entity type B and vice versa. So this is the difference we want to make. Yeah, you can have fields in table A having several related fields in table B, and several related fields in table B, or several fields in table B can have several relations in table A, as you can see. Like in table A field called A1 has a relationship or is related to field B1, B2, and B3 for second table. Field B2 in the second table has two relationships with table A. It is related to A1 and related to A3. That's what we mean. So you can see there are several relationships. So there are several matching entity occurrences in both of the tables, table 1 and table 2, table A and table B. The third way of classifying relationships is according to optionality or participation. Now, optionality in this case refers to the minimum number of entities in a relationship. It can be mandatory or optional. An example is, under the mandatory, we are saying there must be an entity occurrence. So note here, under optionality, we have mandatory relationship and optional relationship. Under mandatory relationship, we are saying there must be an entity occurrence participating in the relationship. Under the optionality, there may be an entity occurrence participating in the relationship, meaning it's not a must. To show optionality, you put a circle or 0 at the optional end of the relationship. Now, let's look at building conceptual data model. How do you build a conceptual data model? That's number 3. The data model that results after conceptual design is called conceptual data model. Here, you choose a notation and design the data model. Most of the differences between models here concern how relationships are specified and how attributes are shown. In almost all variations, entities are depicted as rectangles with either pointed or rounded corners. The entity name appears inside. Relationships can be displayed as diamonds or can be simply line segments between two entities. For relationships, there is always a need to convey the relationship name, the degree, cardinality, and optionality where necessary. Any notation, and I mean any notation selected, must be used consistently. Now, once you're done with the phase 1, you move on to phase 2. In phase 2, here, you do what we call the logical database design. Now, what does this entail? Logical database design entails the process of constructing a database based on a specific database management system and the database model you have chosen. For example, a relational database model. Here, you consider how the data is represented using the structures offered by the database management software. Therefore, logical database design is done as follows. Number 1, you select your database model. Now, what is selecting database model? Here, you choose a collection of concepts and the rules for the description of the structure of the database. Number 2, you map entity relationship diagrams from conceptual data model that you have developed into logical model. You do this by identifying all the entities and relationships as captured in your conceptual data model that you have already developed. So the following is an example of an ERD for a MediSwap school. This is an example. Now, this is similar, almost similar to another ERD model that we discussed in my previous series or presentations in this series. Now here, you can see a full roadmap of my database that I'm going to create or that we're going to create by the title MediSwap School. Here we have the fields, we have the tables, we have the fields in each, and I have identified or indicated which are the primary key, PK, and which are foreign keys. And as usual, any key that is called the primary key in one table, it is a foreign key in another one. That's another table that it is related with. For example, in enrollment table, you have a primary key called enrollment ID. And because the enrollment table is related to the courses table, you can see that we have a field also, which is common there. Now, the enrollment ID here in the elements or in the enrollment table, the enrollment ID here, as a relationship with all the fields. Now, let me repeat. Let me first of all show you which are the primary keys in this ERD. The primary keys are all indicated as PK. So in enrollment entity, that is enrollment table, we have a primary key called enrollment ID. When you look at the courses table or entity, we have a primary key called course ID. In students table, we have the primary key called student ID. In programs table, we have a primary key called program ID. In payments table, we have a primary key called payment ID. In the fees table, we have a primary key called the fees ID. Now, if you look at them, the enrollment table has what we call many enrollments being related to one course, that is course ID. While the enrollments table and the students table have many enrollments being related to one student, that is student ID. In the payments table, the payments table and the students table have many payments being related to one student ID. So many payments being done by one student. In other words, all the fields in the payments table are related to a student ID. Because a single student in the students table whose identification is student ID will be related to all the fields in the payments table, of course, through the student ID. So the student ID here, which is the primary key, is also in the payments table as foreign key. Another case here, we have many courses being related to one program through program ID. So under the courses entity and the programs entity, we have program ID. So under programs, the program ID or primary key is program ID, which is a foreign key in the courses table. So many courses being related to one program through program ID. Between students table and the programs table, we have many students being related to one program, or many students taking a single program. So the relationship here is program ID. Now the program ID is a foreign key, in students table, but it is a primary key in programs table. We also have fees table being related to programs table through what? By having many fees fields being related to one program. So in the fees table, we have program ID, and which is now a foreign key, and it is also a primary key in the programs table. We also have a relationship between payments table and the fees table, where the fees payments table and the fees table are related through fees ID, where fees ID is a primary key in fees, and It is the foreign key in fees ID, and therefore we have many payments being related to one fee record or fee ID. So this is an entity relationship model for a medicinal school. It indicates the number of relationships we can have and through which fields. Number 3, you identify the attributes. Attributes are like the fields. So you set explicit values associated with someone or something, or let me call them the descriptions, which represents characteristics or values about a database relation or an entity. They include 1, the key attributes. What are key attributes? These are attributes which uniquely identify an instance of an entity or identifier, such as a student number or car registration number, etc. So those are called attributes. You can even call them fields, by the way. Now, these qualify to be primary key. So one of them or any of them can serve as a primary key as long as it contains unique values. Number 2, we have what we call non-key attributes. Now, these are attributes or fields which describe a non-unique characteristic of an entity. For example, a name. A name. Another example is here, the color, the model. Now, they are the fields that may contain data that is similar to another field, but not. But the key attribute must have, wherever it will appear, it must have the same data. We also have what we call required attributes. Now, these are attributes which must have a value, or a value must be known for each entity occurrence. Example is a student number. We also have the 4th type of attributes or characteristic, which we call optional attributes. These are attributes which could have a value, or a value may be known for each entity occurrence. Example is an employee, where we have employee's spouse is optional, since not every employee will have a spouse. Composite attribute. This is attribute that can be divided into smaller subparts. These subparts represent the basic attributes with independent meanings of their own. For example, name attribute. We can divide name attribute into subparts where we have first name, middle name, and last name. We also have what we call simple attributes. This attribute cannot be divided into subparts. It is therefore said to be a simple or atomic attribute. Atomic attribute. For example, employee number is a simple attribute. It's atomic attribute. You can't split it. Age of a person is a simple attribute. It is an atomic attribute. You cannot split it. We also have what we call single valued attribute. This is an attribute that can have single value at a particular instance of time. For instance, a person cannot have more than one age value. So that is as simple as that. We have what we call multi-valued attribute. This attribute can have more than one value at one time. For example, a person can have more than 1 degree at one time, or more than one course. Therefore, attribute degree is said to be a multi-valued attribute. There is also what we call stored attribute, an attribute that applies or supplies a value to the related attribute. We also have what we call derived attribute. What's a derived attribute? An attribute, this is an attribute whose value is derived from a stored attribute. Now, these attributes are usually created by a formula or a certain operation or other attributes. Like if you are counting, you are computing certain values from more than one field, what you derive or what you arrive at is a derived attribute. If you generate a field for profit, net value, it means that the content of that field will have been generated from other fields through a computation. For example, age. If you want to know the age of a person, you subtract year of birth from the current year. So what you get under age is a derived attribute. We also have what we call candidate key. This is an attribute or a set of attributes that uniquely identifies individual occurrences of an entity type. We have also what we call primary key. What's a primary key? This is a unique attribute that is used to identify an entity type. For example, entity type student can be identified by a student number. And whenever that number is used in a database, that number will be used to represent that student. We have composite key. This is a candidate key that consists of 2 or more attributes. For example, voter's ID, national ID, and passport ID. So one person will have voter ID, a national ID, and a passport ID. But it's not a must to have the 3. Now, once you have all that, you also need to normalize your database. So number 4 is normalizing the database. So what is to normalize a database? Normalizing a database is the process of organizing the data into tabular format or tables and removing redundant data from those tables in order to improve storage efficiency, data integrity, and scalability. So through normalization, you ensure that you don't repeat fields and data is not repeated. It is done in order to, number 1, make it feasible to represent any relation in the database. Number 2, increase speed and flexibility of queries so that it becomes easier to search for any information. Number 3, normalization frees relations from anomalies. Number 4, it reduces the need of restructuring the relations whenever new data types are introduced. Number 5, it helps avoid repetitive entries or what we call data redundancy. Now, how do you normalize your data? Once you have your fields for all the tables, you proceed as follows. Number 1, make it feasible to represent any relation in the database. Number 2, increase speed. Or in other words, why normalization? What are the advantages of normalization? Number 1, normalization makes it feasible to represent any relation in the database. Number 2, it helps increase the speed and flexibility of queries. That makes it easier to search for any information. Normalization frees relations from anomalies. It reduces the need of structuring the relations whenever new data types are introduced. It helps avoid repetitive entries. This is a repetition of what I have already said. I'm just emphasizing the importance here so that you know that anytime you create a database, you must normalize it. Before you create a database, first of all, develop the fields, the tables. See which fields are in each of the tables, which fields are repeated, and then avoid repetitions all over. If a field is appearing in all the tables, then you can have a central table containing those common fields that are required by more than one field, by more than one table, and then you can now relate or create relationships from there. Number 5, you design the entity relationship diagram. That is a logical data model, and you validate it with the users. A logical data model describes the data in as much detail as possible without regard to how they will be physically implemented in the database. A logical data model is used to explore the domain concepts and the relationships of the problem. This could be done for the scope of a single project or for the entire enterprise. The logical data model depicts the logical entities types, typically referred to simply as entity types. The data attributes describing those entities and the relationships between the entities. Now, to design an entity relational diagram or logical data model, we use the normalized forms and the standard notations to draw the ERD. Such notations include RE95, NDF11X, chain, crow's foot, among others, and in each of them, we make use of the following symbols or elements. So entity across all of them is represented in the form of a rectangle, as you can see. The relationship line is represented as you can see. Now, for the relationship, in chain, you use that diagram you can see there, but in RE85, we shade the lower part, as you can see, and we don't have that symbol for relationship for crow's feet and for index IDF 11x. For optional symbol, you can see the symbol we use for 10, crow's feet, and rain in the 5, and also for IDF 11x. And for one symbol, that's how we present it. For many-to-many relations, we do it in 10 by M. Crow's feet, we use that symbol. For rain in the 5, we use that symbol. And for IDFX, that is IDF11x, we use that symbol. Composite entity, we represent it as you can see under 10 and the crow's feet, and rain in the 5, and IDF11x. For weak entity, we represent it as you can see. Now, the features of a logical data model include, number 1, all entities and relationships among them. Number 2, all attributes for each entity are specified. Number 3, the primary key for each entity is specified. Number 4, foreign keys or keys identifying the relationship between different entities are specified. Number 5, normalization occurs at this level. Lastly, you create what we call a data dictionary. Number 5. Phase 3, or in phase 3, we now do what we call the physical database design. This is the process of constructing a model of information used in an organization based on physical considerations like software and hardware. Now, in physical design, the concern is on how the database is going to be organized in the form of files and what kind of structures you are going to use for efficiency of database processing. Now, the steps for doing that is that number 1, you select the database management software you are going to use. By considering such factors such as cost, features and tools, underlying model, portability, database management software hardware requirements, security, and usability. Number 2, you select the storage devices. Here, you choose the media for storing data, whose data access is faster, has low cost of data per unit, and is reliable in terms of ensuring that data is accessible even after the device failure. Some of the devices that you can consider include appropriate cache, main memory, flash memory, magnetic disk, optional storage, and tape storage. Number 3, you determine the access methods that you're going to use. Here, you identify the specific structures that provides the access method that you want for your database system in order to achieve optimum performance. Now, some of the access methods that you can consider are sequential, the index sequential, and hashing. Number 4, you design the files and the indexes. Now, this entails creating a set of tables and the constraints on those tables from the information given in logical data model. Now, the tables here are designed and their field properties such as field name, data type, and length are specified. Number 5, you determine the database distribution, where you consider the location and number of users for your database. For example, a single user database, in which case the database can be stored in a local computer, or a multi-user database is stored in a dedicated server where users can access it simultaneously, or a distributed database for users who are not within the same location and the organization has several branches. Number 6, you produce the physical model and validate with the users. Now, this is a model where or which specifies all table structures, including the column name, column data type, column constraints, primary key, foreign key, and the relationships between the tables. The steps for physical data model design are as follows. Number 1, you convert entities into tables. Number 2, convert relationships into foreign keys. Number 3, convert attributes into columns. Number 4, modify the physical data model based on physical constraints or requirements. And with that, my dear students and the rest of the learners, we have come to the end of part 4. And note, we are going to implement what we have learned in the subsequent presentations, where or when we shall be creating or designing our tables. You can now continue to part 5 of the 22-part series, in which you are going to learn on how to determine database structure and operations. Congratulations for learning part 4 of 22 on database design concepts in database management system using Microsoft Access and SQL. You can access the rest of the parts in the series as well as other computer or ICT videos by clicking or tapping on Emily Swap ICT YouTube channel below this video. To subscribe to the channel, which is good, especially as a support for the series of presentations you are receiving by tapping on subscribe button below this video in YouTube, that is just below this presentation, if you see that it is not currently reading as subscribed. So if the button below this video does not read as subscribed, kindly tap on it as a way of supporting the production of this series by having it changed to subscribed. If it reads as subscribed, good. Let it remain that way. It indicates that we are already a supportive member of the channel. And remember, subscribing is free. You can also join the channel as a special subscriber if you want additional support by clicking on the join button, and then you follow those set of steps that will be displayed for you. For any further correspondence, kindly write to us through the email emilyswap@gmail.com. Thank you very much for listening to me. Let's meet in part 5 of the series, and God bless.